Hello there, welcome to this video. This is 1-3 and we're going to find limits analytically, looking at algebraic representations of functions and determining the limit. Alright, so the first thing that I do want to cover is when do limits not exist? And I'm going to go ahead and show you a graph and then an equation that can represent it. The first one that is extremely popular or extremely common is when we have a jump discontinuity. And we have already seen examples of this, specifically the topic that we talked about last lesson, which is piecewise functions. So here's a graph and an example where the limit does not exist at 0, and this is a piecewise function. And this function, if we go ahead and made it up, it would be y is equal to x. So I just have x for all x values that are less than 0. And for everything greater than or equal to 0, I could put x squared plus 1. So I just went up one value, and the limit does not exist. Okay, so that's example number 1, a jump discontinuity, or I guess, yeah, it is a jump discontinuity, but the limit does not exist there. Case number 2 is when we have vertical asymptotes. And an example of this, if I just made, let's say, an asymptote here at 2, if I have a function that goes up on the left side of it, and I'll even do if it goes up on the right side of it. The limit here does not exist. It does not exist. And this function would be f of x is equal to 1 over x minus 2 quantity squared. We have an even asymptote there. Okay, if I just had x minus 2 on the bottom, the right side of that graph would go down and it still would not exist, right? The limits from the left and the right do not equal each other. Okay, and then the third case, which is kind of unique here, I'm just going to do a basic square root function. F of x is equal to the square root of x. The limit does not exist at endpoints for an interval. So because the limit from the left does not exist for our graph, y equals square root of x, we do not have a limit. Okay. Now there is a fourth one. It's when we have an oscillating function. Usually those are in trig functions. Those rarely show up, and we most likely will not see them. Okay, but those are the main three. So I want to talk about when we evaluate limits analytically. Okay, so the concept of a limit works for both continuous and discontinuous functions. And the AP exam loves to target functions that are not continuous. That's its favorite, okay? And however, if working with a continuous function, don't overcomplicate the idea of the limit. All you have to do is just find the point on that graph if it's continuous. Again, when working with a continuous function, the limit is the actual point on the graph, okay? And so these next couple of examples, we're going to go ahead and see where the first thing that you should automatically do with the limit, plug it in, see what happens, okay? So let's look at example number 1, where they say evaluate the following limits if possible. So A, what's the limit of 2x squared minus 3 as x approaches 3? All I'm going to go ahead and do is I'm going to plug in 3, and I'm going to see what I get. Okay, so I get 3 squared 9, 18 minus 3 gives us 15. 15, there's the limit. That's it. That's it. Just plug it in, see what happens. B, the limit of 4 to the power of x as x approaches 0. Well, that's 4 to the power of 0, which is 1. The limit's 1. That is it. Not too complicated. The limit of 5 as x approaches negative 2. Well, 5 is just a constant function. It's always 5. So 5 is the answer. Pretty easy, right? We're just blowing through these. D, the limit of x squared plus x plus 2 over x plus 1 as x approaches 1. Now with rational functions, maybe you get a little tense just looking at it, just because, you know, it's a fraction and we tend to do that. However, maybe the first thing you can ask yourself is, can I factor this? Can I break this down? Can I simplify it? And in this case, the numerator is not factorable. So one thing that you should check too is just what's the denominator? And if I plug in 1, we're going to get 2. So we're kind of safe here. But rational functions always evaluate the limits separately. So I'm going to evaluate the limit of the numerator. Notice how I write the limit statement, limit, as x approaches 1, of the numerator. And now when I plug in the values, that's when I can drop my limit statement. So I have 1 plus 1 plus 2, okay, 4. That's the numerator. And now I'm going to evaluate the limit of the denominator of x plus 1. So we get 1 plus 1, which is, oh, I already knew my answer, 2. Okay, so the answer here is 4 over 2, which is just 2. Not too bad. Nothing funny happening. E. Okay, let's go ahead and check on your trig here. So what I'm just going to go ahead and do, sine of x, I'm going to evaluate. What is the sine of pi over 6? Okay, and that's the y value at pi over 6. So we get 1/2. Okay. All right. I'm going to have you pause the video here. Go ahead, try F on your own. Try F, see what you get. Okay, hopefully you gave F a go. Remember, we're going to go ahead and evaluate the limits of rational functions separately. So I'm going to evaluate the limit as x approaches -2 of my numerator, x squared minus 3x plus 1, which this gives us, looks like 4 plus 6 plus 1, so that's 11. I got 11. Okay, and now the limit of the denominator, x plus 2. If I plug in, we get -2 plus 2. Okay, our denominator is 0. So this is equal to 11 divided by 0. 11 over 0. Now 11 divided by 0. Anytime you're dividing by 0, this limit is going to get extremely big. It's going to increase. So imagine having something and dividing by smaller and smaller pieces. And just to kind of illustrate this idea, 1 over 2, think about how much that is. 1 over 3, how much is that? 1 over 4, that's a quarter. 1 over 10, that's a tenth, right? 1 over 100, that's a penny. So do you see as our denominator is increasing here, this is going to be equal to 0. So 1 over infinity is equal to 0. And this idea of 11 over 0 here, that does not exist. I mean, you can't divide by 0. So we're going to say here dne. It does not exist, okay? And this would be tying it back to our case number 2 up here. That is the infinite case, okay? So dne for that one. Hopefully you got that one. Okay, now let's go ahead and talk about some weird situations. In the cases above, nothing of great interest or new happened when we attempted to find the limit. However, that's not always the case. Consider the following limit. The limit of the rational function x squared minus 3x minus 4 over x squared minus 9x plus 20 as x approaches 4. So if I go ahead and if I calculate the limit of the numerator, so the limit as x approaches 4 of the numerator, x squared minus 3x minus 4. And if I plug in 4 here, we get 16 minus 12 minus 4, which is 0. Our numerator is 0. Okay? The limit as x approaches 4 of our denominator this time, x squared minus 9x plus 20. Okay, well this gives us 16 minus 36 plus 20. Hey, that's 0. Okay, so when we attempted to plug in 4, we got 0 over 0. Go ahead, do me a favor. Ask your phone, especially if you have an iPhone, what 0 over 0 is. Let me know what she says, okay? Pause the video. All right, hopefully she told you you have no cookies and you have no friends. That's not true. I'm your friend, okay? So don't be sad. But there's two indeterminate forms. These are indeterminate because we cannot determine anything. 0 over 0 and infinity over infinity. These are the two special cases. The one that appears the most, 0 over 0, okay? Now, what do we do if we get an indeterminate form? We have two approaches to deal with these indeterminate forms. Well, and actually a third one that we'll dive into later on in the course, okay? Example number 1, factor. See if you can get some stuff to cancel. So here's that same problem that we just looked at. And what I'm going to do is I'm going to rewrite my limit statement as x approaches 4, and I'm just going to factor the numerator. Okay, x minus 4, x plus 1. And I'm going to factor my denominator, x minus 4, x minus 5. And lo and behold, look what we have, top and bottom. I have a factor that cancels. Now, hopefully in your pre-calculus course or your accelerated pathway, you recognize that there is a hole at that factor, x minus 4, right? And so that process would be, okay, let's set x minus 4 equal to 0, solve, and hey, at the x value 4, we have a hole. Good, okay, so now what I can do is I can rewrite this limit statement. Not that the hole is like really important here. It's good to know what's going on at 4. Okay, so I reduced, and now I have the limit of x plus 1 over x minus 5 as x approaches 4. And if I go ahead and plug in 4 now, what do we get? We get 5 over negative 1, which is negative 5. Negative 5. Just checking my notes. Yep, that's what I got. Okay, so that's the limit. Factoring took care of that indeterminate form. Okay, here's example B. Go ahead, pause the video, try this one, and I'll show you how to do it in a second. All right, hopefully for this one, you found when plugging in the limit as x approaches 0 that we get 0 over 0, top and bottom. And that's pretty obvious, right? I mean, all these terms here are variables, so when I plug in 0, everything's going to disappear. So what we're going to do is we're going to rewrite this. The limit as x goes to 0, and we're going to factor. I'm going to take out an x squared, it looks like. I have 4x minus 5 over, we'll take out an x squared. If you wanted to put this in standard form, you can go ahead and do that. 8x cubed plus 6. You don't have to. And check it out. My x squared is going to cancel, and it looks like we'll have a hole at 0. Okay, and this is equal to the limit as x approaches 0 of, and when we plug in 0, 4 times 0 minus 5, 8 times 0 cubed plus 6, we get negative 5, 6. Okay, so there you go. That's what you should have gotten for the limit. Okay, and just at this point too, I'll make this kind of note. Never, ever, ever say the limit as x approaches a value of a function is equal to 0 over 0. If you ever have that on your paper, cross that out so the AP Calculus reader does not read that. Some readers are sticky on 0 over 0 equaling 0, 0. You should always evaluate the limit of the numerator and the limit of the denominator separately, as we did here, right? So we evaluate it separately. We got 0. The denominator was 0, okay? And then we went ahead and factored from there, okay? In this example, I mean, we're obviously factoring to determine what the limit is, so I went ahead and I factored right away. But in my initial approach, I would have separated the limits. I would have done the limit as x approaches 0 of my numerator, and then gotten 0, right? Because that's equal to 0. And then I would have and a separate limit calculated the limit of the denominator. Okay, moral of the story, never write equals 0 over 0 on your paper. Okay, that is the first approach, factor. We need to factor in order to determine. Okay, here is a AP Calculus exam question from 2013. Pause the video, go ahead and find the answer to this question. All right, hopefully you went ahead and calculated the limit. And if you calculate the limit top and bottom, you get in an indeterminate form. So ideally, hopefully what you did is you factored and reduced. So we have x plus 3, x minus 2, and in the denominator, x minus 2, x plus 2, with these two canceling. So we have the limit as x approaches 2 of x plus 3 over x plus 2, which gives us 5 over 4. D. D is the answer. So if you got that, good job. Good job. Okay, the second technique. If we're going to go ahead and evaluate a limit, okay, we need to go ahead and learn the idea of rationalizing a numerator, okay? And so I just want to go ahead and really quickly show you my approach to this problem. So they say example 4, evaluate the following limits if possible. So what I would do is I would take the limit of the numerator, the limit of x plus 1 minus 1 as x approaches 0. Now if I do this, I get the square root of 1 minus 1, which is 0, okay? And now the limit of the denominator. The limit as x approaches 0 of x, well, that's just 0. Indeterminate. What do I do? Well, here's where we're going to go ahead and rationalize. And we are going to use the conjugate. Conjugate. So go ahead and write the word conjugate on your notes. Can you say the word conjugate? Good job. Okay, the conjugate. I'm going to go ahead and I'm going to multiply top and bottom by the conjugate of whatever contains the radical. So the square root of x plus 1 over the square root of x plus 1 plus 1. Now, the numerator is going to have some interesting algebra. This is going to rely heavily on your algebraic skills in order to solve this. Okay, so let's go ahead and just check this out. So square root of x plus 1 times the square root of x plus 1. That's just x plus 1. Okay, square root of x plus 1 times a positive 1. Okay, that's plus the square root of x plus 1. Now I have negative 1 times square root of x plus 1. So minus square root of x plus 1. And negative 1 times a positive 1 gives us a negative 1. Okay. Now, if you did this correctly, a lot of things should cancel, right? The whole point of this is to kind of clean up, believe it or not. Trust me, we're actually cleaning, right? It always gets worse before it gets better when we multiply by the conjugate. Notice, so those radicals automatically cancels. That helps us. Okay, and then check out here, I have the plus 1 and the negative 1. That cancels. Hey, what's left? It's just an x. It's just an x, okay? And then in our denominator, always just keep your terms separated. What we just multiplied by, don't even bother multiplying it. It's really that numerator that's messy, right? So if I go ahead and rewrite this, I know you're hating me right now. It's okay. I will bear that responsibility. But check out now what happens. What do I have? Top and bottom. Hey, I just have an x, top and bottom. That cancels. Okay? So now I have the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. And if I plug in 0, we get 1 over square root of 0 plus 1, which is just 1, plus 1, and that's 1/2. So the limit is 1/2. All of that for 1/2? Yes. Yes. Okay, that's multiplying by the conjugate. All right. B. Trust me, this is an indeterminate form. We're going to go ahead and use the same idea. We're going to multiply in the conjugate. Please pause the video, pause me right now, and then I'll walk through this here in a moment. So I want you to try. First of all, what is the conjugate? What is the conjugate? Okay, hopefully you're multiplying by the square root of x plus 5 plus the square root of 5. That's the conjugate. The same two terms, it's just a different operation between the two terms. Okay, and I'm going to multiply top and bottom. Okay, so go ahead and pause me if you have not already and evaluate this limit. Okay, so if you went ahead and evaluated the limit, the numerator, after multiplying this, you should have gotten x plus 5 plus root 5 root x plus 5. You could merge those together, but I wouldn't. I'm just going to keep them separated because look what happens. Oh, I have a positive root 5 times x plus root x plus 5 and a negative root 5 times root x plus 5. So I wonder if those are going to cancel. Okay, and then a negative root 5 times a positive root 5, that gives us negative 5. Okay, and then our denominator, like I said, just keep them separated. So don't even bother mixing those together. And this is what you should have gotten. Right? I know, it's heavy, it's dripping with algebra. Ugh. Okay, what cancels? This is the best part about being a mathematician, canceling stuff. Those cancel. Yes, sound effects are mandatory. Hey, and I have opposite 5s. Okay, pew pew. All right, now if I go ahead and rewrite my limit, the limit as x approaches 0, x over x times the square root of x plus 5 plus root 5. Our x's cancel now. Okay. And we have the limit as x approaches 0. Do you guys see how I'm doing all this algebra and I'm still carrying that limit statement with me? I'm still writing the limit as x approaches 0. Yes, you have to do that until I plug in 0. Until I plug in 0, which I'm finally at that stage now. So the square root of 5 plus the square root of 5, I'll plug in 0. Square root of 0 plus 5 plus the square root of 5. And we get 1 over, it looks like root 5 plus root 5, which is 2 root 5. If you're not cool, that's not cool, Schwarberg. I don't get it. That's root 5 plus root 5, right? That's 1 over 2 root 5. There is the limit. Those are not fun. They don't appear that often, but, I mean, you need this specialty tool in your tool belt, okay? All right. Now, some of those tools are more extensive than others, but we do have a special tool coming. The AP test, the one that it loves to use, is called L'Hopital's rule or L'Hopital's theorem. We'll go ahead and we'll learn that later. We'll learn it later. It'll make your life easier. But we haven't learned it yet, so we can't use it. Ooh, suspense. Maybe we'll learn it next time. All right, in this video, you should have learned to evaluate limits algebraically or analytically. Plug in the limit value. Plug it in, see what you get. If you get an indeterminate form, 0 over 0 or infinity over infinity, what you're going to have to do is you're going to have to factor, cancel stuff out, and solve. Otherwise, if you have a radical in there, you're going to have to go ahead and multiply by the conjugate. That's what we learned in this video. Hope you had a good time. Hope you learned something. Like and subscribe. I'll catch you next time. Peace.